Good morning. Okay, we will continue where we left it yesterday. Let me put it's complaining. Okay, so I got it. Okay, we have seen yesterday that the sun cooks heavy elements inside, and in the process of cooking these heavy elements, it produces lots of neutrinos. They come in different chains. We have seen that they come in the PP chain, they come in the PEP chain, in the beryllium-7 chain, in the boron-8 chain. The important thing to notice is that they are either a continuous spectrum or a monochromatic spectrum, and this will be important for some cases, okay? So we have seen also that they have different energies. They span energies from well below the MeV to above the MeV, 5, 10 MeVs. And therefore, different experiments in the earth, they have different technologies, different sensitivities, and therefore they measure different neutrinos. Neutrinos coming from different chains. This is what I mean with different neutrinos. The gallium experiments we were going to talk about today measures PP neutrino, the lowest possible energy neutrinos. The experiments we measured yesterday, SNO and Super Kamiokande, they have a threshold of 5 MeV, so they measure boron-8 neutrinos. But the common feature we have seen with all the experiments measuring solar neutrinos is that they have seen different suppressions. Different experiments have seen different suppression. No experiment seen all the neutrinos they were expecting based on the calculations of the solar flux. And we decided to explain this as it worked with the atmospheric neutrinos, to explain this with the oscillations. But we also found out that we have to go, the kinematic phase is huge. Okay, so we are in the coherent regime. We applied all we have seen with the incoherent regime, and we've seen yesterday that while low energy neutrinos, this means PP and beryllium-7 neutrinos, they have a survival probability of, roughly speaking, 60%. The beryllium-7 and the boron-8 neutrinos have a survival probability of 30%. This is quite puzzling because this will mean that boron-8 neutrinos are produced essentially as a second mass eigenstate. 90% of the electron neutrino content is on the second mass eigenstate, 10% in the first mass eigenstate, while for the PP and the beryllium-7 neutrinos, 70% is on the first mass eigenstate and 30% in the second mass eigenstate. And we say that maybe this is because I'm not producing neutrinos in vacuum, but I'm producing them in the center of the sun. So maybe, and just maybe, the fact that they are producing neutrinos in a dense medium may change the coherent superposition of mass eigenstate I'm producing. This idea is not new. This was from the late 70s, I think, beginning of the 80s by Mikeyes and Smirnov, and they have proven that if you produce neutrinos in matter, you get a different coherent superposition of mass eigenstate. So we are going to work this out and see what is the difference and what we can learn from that, okay? So we are going to start with the Schrödinger equation, which I call it there the neutrino evolution equation, but this, you have seen this many times. This is just the Schrödinger equation, and this H, the Hamiltonian here in the mass eigenstate basis, is just the energy of the neutrinos. But I'm going to assume now that my neutrinos are extremely relativistic. So this can be written as the momentum plus a small correction over the mass. I'm going to assume now they have all the same momentum, but there is something to be said about that. I have to diagonalize this matrix on the blackboard. So this will mean that I will do, you don't have to do all the things that I'm going to do, but I'm going to do it anyway. But you can notice that anything which is proportional to the identity matrix will produce only a global phase. Just look at the Schrödinger equation. So I will remove, and global phases we have seen yesterday. Global phases, the absolute value of a global phase is 1. So they won't play any role into oscillations. So I will just throw away, no mercy, anything proportional to the identity matrix. So I will write this as something proportional to the identity matrix, which I will write completely ignore, and something which is not proportional to the identity matrix, which is the only thing I will not keep. Now I want to include to these Hamiltonian interactions. This means I have to move from the mass eigenstate basis to the interaction basis, and I move this easily by hitting left and right with a mixing matrix, as I have done before. There you are. And this is the diagonal mass in the mass eigenstate basis in the flavor basis. Again, because this will be important, I started with a mass which is diagonal in the mass eigenstate basis, and this mass takes this form in the flavor basis. This will mean that if at some point, let's say in 2 slides, we face some matrix which can effectively be written in this way for some effective mixing angle and an effective mass difference, we immediately know we have diagonalized this matrix. We immediately know what are the mass difference and the mixing angle in a medium. This is why I'm writing this in this way. Okay, so let's start with this matrix and let's start adding interactions. In the sun, I have, my neutrinos have charge currents and neutral current interactions. Okay, charge current interactions are only enjoyed or suffer, whatever, by electron neutrinos because the sun is made of matter. I have electrons there. I have no muons or taus. This means only electron neutrinos or electron antineutrinos have charge current interactions, and these charge current interactions, of course, are going to be proportional to the Fermi constants because they are weak interaction and to the number of targets I find on my way, the number density of electrons. They are attractive for neutrinos and repulsive for antineutrinos. This is the plus minus sign. I also have neutral current interactions, but as we said yesterday, neutral current interactions are flavor blind. This means they are the same for all 3 flavors. I can just ignore that because this will be proportional to the identity matrix. Okay. However, if I would like to include at some point sterile neutrinos, I cannot play this game any longer because sterile neutrinos will not have neutral current interactions, and I should have to include this term as well. As I'm caring only about active neutrinos, I happily discard this term because I'm assuming there are no sterile neutrinos here. Okay, so we have to include this term, but again, let me write this in something in a little bit more symmetric way, as removing something proportional to identity matrix to write it something in this way. But again, I don't have any need to do that. It's just for me to diagonalize this over the slides. It's not that you need to do that. So now let's include this term to the mass term we have written before, and there you have, and it would be possible in principle to diagonalize this term if you identify this matrix with this one. So we have already diagonalized it by inspection. Just by looking, we have already done that. Just by identifying this, the mass, the mixing angle in matter and the mass difference in term, we have already diagonalized this matrix. So there are a lot of things to be said about that, okay? First of all is that if the mass difference in vacuum is 0, the mixing angle is unphysical, okay? So we start assuming from the very start that this angle is physical and the mass difference is different from 0. But if the mixing angle were 0 in vacuum, there is nothing you can do in matter, okay? The mixing angle will remain being 0 in matter because there is an, you can see that the product of the sine of 2 times the mixing angle times the mass difference is an invariant. It takes the same value in matter and in vacuum. The second thing which is interesting here is this minus sign. This minus sign opens the door to cancellations. This means there is a regime where I hit a 0. If I hit a 0, this will mean that I reach a mixing angle of maximal mixing, pi/4. Okay, this is a resonance behavior. No matter how small my angle is, there is a regime where it gets amplified to maximal mixing. This is not going to be so spectacular. We are going to see that there are no neutrinos in the sun to see that. But on top of that, the mixing angle in vacuum is not so small to begin with. So it's pi/6. So the enhancement is not spectacular, but it could, the resonance is still there. But with all the things we have written, now that we know the mass difference in a medium and the mixing angle in a medium, we can take all what we have learned yesterday and get the appearance probability, the disappearance probability, whatever you want, by replacing the expression we worked out yesterday for the appearance probability by replacing the vacuum values by the corresponding ones in matter. Here, you have seen that I have written 1 minus the survival probability, which is a very perverted way of writing the appearance probability. Okay, it's not only because I'm very perverted, it's not only because of that, it's because I have been avoiding, I will keep avoiding 5 minutes more to say to what neutrino my electron neutrino is oscillating into. This is why I'm writing this as 1 minus the survival probability. So for the time being, I'm avoiding this question. my electron neutrino is oscillating into something, but I haven't said into what yet. Okay, this is why I'm writing this in this way. Okay, but let's go back to the mass difference and the mixing angle in matter. So you can see there that the mixing angle in matter is larger than the mixing angle in vacuum. No, I don't know why I thought that this was particularly enlightening, but if you go there, you see, let me show. Okay, if you see there, you can see by dividing this equality by this equality that the tangent of 2 times the mixing angle in matter is equal to the sine of 2 times the mixing angle in vacuum divided the cosine of 2 times the mixing angle minus something. Okay, so you see that the mixing angle in matter is larger than the mixing angle in vacuum. For some reason, I thought you can see it there. Okay, this will be important later. But then we have this minus sign, this cancellation, and this opens up the possibility of 3 different regimes. The first, of course, is the mass terms are negligible, the interaction terms are negligible as compared to the vacuum contributions. This is the quasi-vacuum regime, where the mass difference is exactly what you would get in vacuum, and the mixing angle is exactly what you would get in vacuum. And this is exactly what happens to the lowest possible energy neutrinos, the PP and the beryllium-7 neutrinos. This is what happens. Then we have the resonant regime, where the mixing angle goes to pi/4. Unfortunately, there are no neutrinos in the sun to see this happening. This is the only place you can see nature miss an opportunity, okay? It is impossible to believe, because nature would take advantage of any opportunity, does not have neutrinos in the sun to enjoy this. I mean, I cannot understand. Anyway, this is what happens. Then we go to the matter-dominated regime, where you essentially, the mass is essentially given by the interaction, and the mixing angle becomes approximately pi/2. And this is what happened with bottom-made neutrinos. You essentially produce a mass eigenstate. The mixing angle is pi halves. Okay, so now we can understand how hard, how nice, how good is the life of a bottom-made neutrino. For that, I'm going to introduce a notation that I will keep till the very end of my lecture, till tomorrow. Okay? So, in this, so I'm going to draw boxes. Each of these boxes represents a mass eigenstate, and the color pattern inside is how flavor is distributed among these inside this mass eigenstate. So in principle, as we have been working only with 2 flavors, I'm allowed to paint only 2 colors. So let's say black is electron neutrino and pink is whatever is not electron neutrino. But we have seen yesterday that muon neutrino and tau neutrino almost maximally mix. So I will take the liberty to paint whatever is not electron neutrino, half muon neutrino, half tau neutrino. Okay, and this is the answer to what my electron neutrino is oscillating. It's oscillating into an almost maximal admixture of muon neutrino and tau neutrino. So my bottom-made neutrino is born at the center of the sun, essentially as a second mass eigenstate. All the electron neutrino content is in the second mass eigenstate, and it starts traveling the sun in order to leave the sun. Remember that my neutrino is a weakly interacting particle. Its mean free path is way larger than the mean free path of the photon, for example. Okay, but the sun is getting less dense, and the traveling inside the sun is perfectly coherent. So my electron neutrino, my second mass eigenstate, starts sending electron neutrino content to the first mass eigenstate. By the time my neutrino reach the core of the sun, already 0.5% of the electron neutrino content is on the first mass eigenstate. But there is a lot of sun still to travel, okay? By the time my neutrino leaves the sun, effectively leaves the sun, cover all the sun, it's done. Already 2/3 of the electron neutrino content are on the first mass eigenstate. And exactly in this way, exactly identical in this way, it arrives to this Earth, because we have seen that the travel from the sun to the Earth is perfectly incoherent. So there is no exchange of electron neutrino content between the 2 mass eigenstates. All the exchange took place in the sun. Okay, so however, we have seen this modulation of matter effects. Go ahead.
I think there are shouldn't there be a third massing state as well now
It's the
if
copy
we
here. I don't need that to explain because there is almost not. In fact, there will be a third mass eigenstate, but I'm working only in 2 flavors. There will be a third mass eigenstate
okay.
soon enough. Okay, so we have seen this modulation of the electron neutrino survival probability for boron main neutrinos and PP and beryllium-7 neutrinos in different experiments. We would like to be sure we are not missing anything, okay? We would like to be sure that this modulation happens all in the same experiment, and we have seen that is in the Borexino experiment. Borexino experiment is experiment located in Gran Sasso lab in Italy, which was meant to measure the beryllium line, the monochromatic line of beryllium-7 neutrinos. These are below the MEV, but regardless of whether you want it or not, they can see also boron main neutrinos and PEP neutrinos, and Borexino by itself was able to show the modulation. So Borexino is blue, red, and orange here. And so Borexino by itself has seen the modulation of the survival probability. So after Borexino, we are pretty sure neutrinos from the sun to oscillate. However, I was not 100% honest. I show you these as the solar pair, how flavor is distributed among the 2 mass eigenstates will make the solar mass difference. However, the only thing we have used is the sine square of 2 theta. And as you know, the sine square of 2 theta, the sine of 2 theta, we used it yesterday, is 2 times sine theta cosine theta, okay? So I will get exactly the same sine of 2 theta if I exchange sine and cosine. This is just reflecting my angle over pi over 4. So if this is pi over 4, what divides the first and the second octant, if you have an angle larger than pi over 4, there should be an angle smaller than pi over 4, where you exchange sine and cosine, which has the same sine of 2 theta product. And the other way around, if your mixing angle is smaller than pi over 4, there is another angle, the reflection around pi over 4, which is just exchanging sine and cosine. So the thing is, how can I be sure is this combination or not that combination? After all, they both have the same signs of 2 theta, okay? It's just, I'm exchanging sine and cosine. I'm exchanging the electron neutrino content from the first to the second mass eigenstate. It's not a big deal. How can I be sure which one of these 2 it is? And why do you care? We care because we can measure it, okay? We can measure it because we have said that the mixing angle in matter is larger than the mixing angle in vacuum, and the Snow experiment can measure that. Why we can measure that? We have seen that this propagation is perfectly incoherent. It's just a fraction of neutrinos produced in the first mass eigenstate times cosine square plus the fraction of neutrinos produced in the second mass eigenstate in the sun times sine square, and can be written in this way. Well, if the mixing angle is smaller than pi over 4, the cosine of 2 times the mixing angle is a positive number, okay? This is smaller, 2 times is smaller than pi half. This means the cosine is positive. However, I have, as the mixing angle in matter is larger than the mixing angle in vacuum, I have no idea whether this contribution is positive or negative. I just don't know. I cannot say anything. However, if the mixing angle is larger than pi over 4, already the vacuum factor is negative. So the matter factor is even more negative, if you can be more negative than a already negative number. But the important thing is that the sign of this contribution, the net sign, is positive. So the survival probability is bounded to be larger than half. However, we have measured it by the Snow experiment. We know it's a third. So we know is the mixing angle is smaller than pi over 4 and not larger than pi over 4. Okay, we have seen this. Okay, so there are more fun things you can do with neutrinos. There are a lot of fun things we can do with solar neutrinos. I don't have time to cover them all. So I put my favorite one, which is day-night asymmetry. We detect neutrinos day and night. Okay, so we detect neutrinos when they go directly to our face, exactly as photons. Okay, they travel. And we detect neutrinos, they travel 2 times the radius of the Earth before hitting the detector. Okay, of course, these 2 times the radius of the Earth as a length does not make any difference. The distance of the Earth to the sun is humongous. And besides, the oscillations are average to, the kinematic phase is average to a half. So the precise distance covered is irrelevant. What is relevant is once neutrinos enter into the Earth back, solar neutrinos start traveling inside the Earth back, they have matter effects, they regain coherence. And when they regain coherence, there can be exchange of electron neutrino content between the two mass eigenstates. And I can see that. Okay, of course, the distance is not huge to get a strong effect. It's a few percent effect, but I have seen that. It has been measured. So we are pretty sure this is what's going on. And of course, we have been spectral distortion. We have seen the modulation of the survival probability as a function of the energy. We have also seen seasonal effects. So we are pretty sure neutrinos come from the sun. Okay, so the summary of all my solar neutrinos is we have seen flavor transitions. So we are sure that neutrinos from PP and beryllium-7 neutrinos, they behave as if they are produced in vacuum. With bottom-main neutrinos, they are produced as if they were in matter, completely dominated matter regime. But remember, we have not seen the oscillations. We have seen only the flavor transition. And this is the mass difference than the mixing angle you can get from these experiments. However, we would like to see the oscillation, okay? We would like to be sure we are not missing anything. We would like to reproduce that. And these are MEV neutrinos. It's pretty easy to get for free. You can get electron neutrinos from reactors. There is one caveat. A reactor produces antineutrinos, the sun produces neutrinos. But if you believe that CPT is a good symmetry, it's up to you. You know, I'm going to advocate for CPT violation, but tomorrow probably. So if you believe that CPT is a good symmetry, neutrinos, antineutrinos behave in the same way, and you can check neutrinos using antineutrinos from a reactor. But now you want to be sure you see the oscillation pattern. Not this time you want to miss the oscillation pattern because you are designing the experiment. So you want to design your experiment so that the kinematic phase will be in the ballpark of 1. Okay, let's do that. We want the kinematic phase to be 1. The mass difference is 10 to the minus 5. The energy is 1 MeV, but this would mean the distance is 100 kilometers, 10 to the 5 meters. So if you are going to place a detector 100 kilometers away from a reactor, you better be sure you have not one reactor, but several of them. Otherwise, you will be happy with your detector, but you will get no signal. Okay, the signal dies 1 over distance squared. And there are not that many neutrinos coming from a reactor. Okay, look at you where you live. Okay, there should be okay, if you live in Europe, it's more difficult. But if you live in France, for example, no matter where you live, there is a reactor 100 kilometers away from where you are. Okay, and you wouldn't ever dream about putting a detector there 100 kilometers from your reactor because you are getting no signal. However, this is what the Kamlan experiment was done in Japan, of all places where you can have tons of reactors in Japan, you know. So in Japan, in what used to be the old Kamioka mine, when I told you this story, which started with atmospheric neutrinos, the first experiment to measure atmospheric neutrinos was Kamioka before Kamioka grew up to become Super K. Okay, this is Kamlan, is a fantastic 1 kiloton liquid scintillator detector, which is located in Japan and is sensitive not to 1, but to 17 different reactors, including one top secret reactor from North Korea. So Kim Jong-un, watch out, we are seeing your neutrinos. He does not care much, okay? So all the reactors go from less than 100 kilometers to over 1,000 kilometers, but honestly speaking, most of the distance comes from 180 kilometers. Of course, Kamlan was not the first reactor experiment to be done ever. Okay, we have been doing reactor experiments since the beginning of the time. Kamlan is different because Kamlan, all the reactors before Kamlan were very close to the reactor, meaning less than a kilometer from a reactor. Okay, Kamlan, and they are, if you know that if you are less than a kilometer from the reactor, the kinematic phase does not have time to develop, so the survival probability is essentially 1. we will see that it's not essentially one, but let's say it's one. Camlan is just sitting at the right place, okay? At the right place where you expect to see oscillations, and Camlan have seen a beautiful oscillation pattern. So after Camlan, we are sure neutrinos do oscillate, okay? They do oscillate with a mass difference, which is around 10 to the minus 5 electron volt square, and a mixing angle, which is roughly speaking pi over 6, okay? So this is, probably you have seen, this is Camlan, this is solar neutrinos, and depending on the year, there is more or less tension. And I'm gonna explain this again tomorrow. I mean, the problem with solar neutrinos is that the chi-square is especially flat in this direction. So, but in principle, there is some tension between what Camlan is seeing, what solar experiment neutrinos are seeing. Okay, so now we have seen all the solar neutrinos and the atmospheric neutrinos. It's time to put the picture together. We know that we have 3 neutrinos, and we know that we have 2 mass differences. One which corresponds to atmospheric neutrinos and which corresponds to solar neutrinos. So obviously there are 2 ways of ordering that. The atmospheric mass difference on top of the solar mass difference, or the solar mass difference on top of the atmospheric mass difference, and they have a name. One is called normal ordering, and the other one is called the inverted ordering. But just this is a name to say whether the state with the smallest electron neutrino content is the heaviest or the lightest. This is the difference essentially between the 2. Here, the state with the smallest electron neutrino content is the heaviest. Here is the lightest. People like to talk about that. Also about the sign of the atmospheric mass difference. Here, the sign of the atmospheric mass difference, understood as m3 square minus m1 square, is positive, here is negative, okay? And we have, of course, if we have 3 neutrinos, a mixing matrix regarding oscillation has 3 angles and 1 phase. We know that there are 2 additional phases, but we also know that they will play no role when the 2 marginal phases will play no role in oscillations. So far we have been talking about 2 angles. We have theta 23, which is the atmospheric angle. We say it's about pi over 4. And we have the solar angle, which we say with the one we have mentioned, which is approximately pi over 6. There is a third angle, the reactor mixing angle, we haven't mentioned quite yet. This is not quite true. This is the angle, which was the last one to be measured, the one which I said is the major breakthrough of 2012. It was measured, and it was measured to be different from 0. And we know it's roughly speaking pi over 20. And this is the angle which makes the Dirac phase physical. If this angle were 0, this phase will be unphysical. This is why we are saying this angle opened the race for CP violation in the neutrino sector, because the other 2 were known for quite some time. Okay, now that we know that, okay, we can see what are the values of these parameters. Okay, good for you. There you are. Okay, so this, as I told you, this you have to do a global field to all the existing experimental data. These are done by phenomenological groups. I'm gonna use all the values from the group of Valencia. You can recover there. Here you have the 1, 2, and 3 sigma ranges for all the parameters. And if you like, this is the way I prefer to see data, the chi-square profiles. Blue corresponds to normal ordering, and purple correspond to inverted ordering. So you see that there is some data favors normal ordering. We are not quite sure yet, but it seems it's normal ordering on top of not inverted ordering. The nice thing to see is the last angle to be measured, theta 13, is the most precisely measured now, is from the 3 angles. And one more thing, I told you many times that the atmospheric mixing angle is approximately speaking pi over 4. We know it's not exactly pi over 4. We don't know yet whether it's slightly larger than pi over 4 or slightly smaller than pi over 4. Some people call it the octant problem. We don't know which octant it belongs. It seems that it's the second octant that is slightly larger than pi over 4, but again, the evidence is not conclusive. I included here in this column what the next generation experiments are gonna bring. Okay, so it's precision to most data is precision, and I put here what is official about CP violation. Probably you have heard there is a claim. I'm going to talk about this claim and say why you have to take it with a grain of salt, that CP conservation, the delta phase of 0 is ruled out at 3 sigma. Okay, it's a very perverted game here. So, but at least we are going to be sure in the next couple of years. Okay, so this is what we know, and this is how we extract the information. So I put there where the main contribution from each experiment comes, but also you have subletting contribution from other experiments. So for you to see that why you need a global fit to all the parameters. Okay, so far I have described what we consider solid pieces of experimental work. All the experiments that fit, all that for one reason or the other is accepted as common knowledge by the community. Now let me talk about these experiments that do not fit. But first, let me tell you that when I entered this field 100 years ago, okay, so there were two anomalies, which one is called the solar neutrino problem and the atmospheric neutrino anomaly. Okay, nobody now talks about the solar problem or the atmospheric anomaly or whatever, because they are solid pieces of physics. Okay, you never heard about the solar neutrino problem. In my time, there were huge arguments about there was or there wasn't a problem. Okay, so the thing is, the lesson to be learned is that I'm going to show you some anomalies. Some of them may go away. We have seen this happening before, but maybe some of them in 20 years from now will be knowledge of physics beyond the standard model that we have not yet understood. Okay, so let me first name the anomalies and put them in context, and then I'm going to go each of them in detail. The first anomaly I'm going to do, by the way, in inverse chronological order. So this one is the latest one, which is not that it's 10 years old approximately, is the reactor anomaly, and it was, let's say, 3 sigma anomaly associated to reactor neutrino experiments, to those experiments which I mentioned with Kamlan, who were very close to the reactor and didn't have any ER detector, whose distance to the reactor were less than 1 kilometer. Then it's the mother of all the anomalies. The anomaly associated to the LSND experiment, which is mid-90s. The LSND experiment is a story on its own, then it's mini boon, and now will be micro boon. It's, let's say, a 5 sigma anomaly altogether. But this is the first appearing experiments. LSND was the first appearing experiment. Now we have a lot of appearing experiments. By that time, mid-90s was the first one. They found the electron neutrinos in an otherwise muon neutrino beam, and I will describe this in detail and why it derived in mini boon. And the last, this is the underdog of all the anomalies. This anomaly was there forever, essentially. It involves solar neutrinos, and it's there since the 80s. And I call it the underdog of all the anomalies, and I'm going to explain you why. Because in the last years, it didn't even make it to the list of the anomalies. People were ignoring it, okay, for quite some time. It was ignored for 15 years, okay? So we are going to talk about that. Okay, let's start. Okay, let me say you something before that. So if I want to explain these anomalies with oscillations, they need different mixing angles. Okay, each of them needs a different mixing angle, but they all need a mass difference of the order of 0.1 to 1 electron volt square. And we have seen we have two mass differences. 1 10 to the minus 5 electron volt square, the solar mass difference, 1 10 to the minus 3 electron volt square, the atmospheric mass difference. So no matter how creatively you add these two numbers, you will never make it to 1. Okay. So if you want to have a mass difference of 1 electron volt square, you need extra state. You need sterile neutrinos. This is the common feature of all these anomalies. So let's start with the reactor anomaly. The reactor anomaly, as I told you, involves all the detectors, all the experiment who has no near detector, who are very close to the reactor, means less than 1 kilometer. So in all these experiments, you calculate the ratio of observed over expected events. So this means you need the number of expected events. This means you need to calculate the number of neutrinos you expect to find from a reactor. Okay, neutrinos from a reactor come from the fission products of uranium-235, uranium-238, plutonium-241, plutonium-239 also. Okay, so there are two methods to calculate the flux of the neutrinos you expect from a reactor. One is called the summation method, and the other is called the conversion method. in the summation method, as the name says, you have to sum over all the possible beta branches. But there are over 1,000 beta branches, okay? And you know what happens. Nuclear data tables may be inaccurate or incomplete. In the conversion method, you convert the observed spectra in the reactor to neutrino spectra. Okay, and where you observe the spectra, you observe uranium-235 and the 2 plutoniums in the ILL in Grenoble, the Langevin Institute in Grenoble, and the 238 in the neutron source from Garching in Germany. So you convert these into neutrino spectra. So you get the gut feeling that the summation method is more complicated and more prone to error. Not to say that the other one is any easy, it's not, okay? But you get this feeling. So in 2012, Patrick Huber and Mueller independently recalculated the flux of neutrinos you expect from a reactor using the conversion method. And they found that this flux was underestimated. Okay, you should be getting way more neutrinos, way more. You should be getting more neutrinos than the one you were actually getting. And then, they were missing essentially 7% of the signal. The significance was, let's say, 2.3 sigma. This was a big hit in the community, and the situation remained confusing, to say the least, till 2018, where a different group, STN and collaborators, calculated using the summation method, the flux of neutrinos you expect from a reactor, and they got a 1.2 sigma anomaly. This means you are not missing any. Okay, 30% of the time you are 1.2 sigma away from 1. Okay, so this is no surprise. However, exactly the same year, yet another group, and collaborator, recalculated the flux. There was a very ongoing discussions, a lot of attention going on there, using the summation method. And they essentially agree with Huber and Mueller, except that the error bars were exactly the same size, but the central value went a little further down. So the anomaly went this time to almost 3 sigma. There were a lot of arguments about whether you were controlling or not the fuel of the reactor. And then 2021, a new group, Kopaikin and collaborators, recalculated the flux again using the summation method, and they found that you are not missing anything, okay? That you were 1.2 sigma from the expected numbers. So we can tell you, okay, there were a lot of debates since then till now. So although the reactor neutrino anomaly has never been pronounced officially dead, I think it's fading away, okay? Still, there are people working on that, but I think the consensus in the communities that we are not missing anything, okay? There is nothing there to worry about. Still, there are people who change their eye. If you talk with some people, say that this calculation is wrong, but I mean, I'm no one to tell, okay? I've never done this calculation. So let's go to the nicest one, LSND. You know, in this field, we don't have that many bloody stories, okay? Essentially none. This one is one of those, okay? This is a nice story. LSND is, I said, it's an experiment in Los Alamos. They were a very short baseline experiment, 30 meters, 42 MeVs. And they find, as I thought, there were like 2 separate experiments, pions in flight and pions at rest, and they found electron neutrinos in an otherwise what should be a muon neutrino beam, and the collaboration split over the result. They were back-to-back papers. Half of the collaboration said they found neutrino oscillations, and half of the collaboration, the second PRL, said they were not finding anything. Okay, so the situation was confusing. Okay, so it's true that they were finding something consistent with oscillations in the anti-neutrino channel and not consistent in the neutrino channel. The situation was really confusing. And so what do? We are a serious community, and then we set up another experiment, okay, to sort this out for good. And the another experiment is the minimum experiment. The minimum experiment is half a kilometer, half a GeV. So you see, it's completely different. The other one was 30 meters. Now we are talking about half a kilometer. The other one, 42 MeV, now half a GeV. The only thing they have in common is L over E. It's exactly the same L over E. So if you find something consistent, minimum and LSND, this something has to be oscillations. There is no other way out. This is the good news. The bad news is Minimoon has problems on its own. So Minimoon couldn't completely exclude LSND in the neutrino run, but exclude some part of it in the antineutrino run. But lo and behold, Minimoon has its own anomaly, 5 sigma anomaly, this time in the neutrino channel and not in the antineutrino channel. But you know, mathematics is very elastic field. So if you go and minimize your chi-square, there is a minimum of your chi-square. Your chi-square always has a minimum. Okay, so in the minimum of your chi-square, you can make it compatible minimum and LSND. This is face value. When you look inside to see what it has inside, you find that the chi-square per degree of freedom is above 2. So you know that what this is saying is the analysis is inconsistent. Okay, you can minimize whatever you want, but analysis is inconsistent. So as I said before, we are a very serious community. What we do, we set up a third experiment. Okay, so there you are, microboom. Okay, microboom experiment is part of Fermilab short baseline neutrino program. It consists of 3 detectors, 400, 600, and 1.2 kilometers. Microboom is supposed to have the last word about LSND and miniboom. However, do not hold your breath, because it has been shown already last year that microboom won't be able to completely rule out this region of parameter space at the verge of minimum sensitivity where they claim they have the anomaly. So the situation may be confusing from in 10 years from now, we don't know. But I mean, if you believe, I mean, these are, I mean, I'm making them laughing stock, but this is not true. They are extremely serious people and they have done a very serious analysis. They have what they have. So there may be something going on there. They claim they have a signal at 5 sigma level, okay? So it may be there. So this is the gallium anomaly. This is, let me tell you why I call this the underdog of all the experiments, because this is a very old anomaly nobody ever cared about. For you to get an idea how old this is, SAGE stands for Soviet American Gallium Experiment. So you get the idea, okay? So the key point here is, okay, they capture neutrinos in gallium. But the key point in this experiment, as in any solar neutrino experiment, is how you calculate, how you calibrate your detector, how many neutrinos you expect. The sources you use to calibrate your experiment are essentially all your experiment is gonna get. Your experiment will be limited by how you calibrate your experiment, and they have used these chromium things to calibrate. So what they have found is when you discount the oscillations which you know happen, you still miss 15% of the signal. So the ratio of observed over expected events is 0.85. What did we do? Okay, we blame the nuclearis. What do? We blame someone else. Okay, this is the standard strategy. We say, okay, our deficit is clearly because we are overestimating the capture rate. This is where the deficit comes. And where it comes, it's because these people have calculated wrong the cross-section we use to calibrate the detector. So go back and do your calculation correctly. What's the problem? Watch what you wish. They did this, okay? They recalculated the cross-sections, and 2 independent groups of extremely serious people have seen that the cross-section, at least they agree with the result. The situation can only stay or go worse, okay? So the situation remained this way for quite some time till we did a new generation of experiment. The best collaboration decided to redo the analysis, to redo the experiment, but with technology 30 years better. And what they have found? They have found that the error bars shrunk a lot, as you would expect with a new technology, but the central value remains there. So the anomaly now is 5 sigma, and you should start taking this seriously into account. The bad news, okay, it depends on you whether these are bad news or good news, is that this cannot be explained away with oscillations, okay? This cannot. Because we already know that if you want to explain this with oscillations, the mixing angle we need is huge. And we already know that solar neutrinos, they are not sterile neutrinos produced in the sun this amount. Because we have measured the total flux of neutrinos we have seen from the sun with the SNOW experiment, for example. So if there is something going on there, which probably there is, this is not related to oscillation. It's still related to neutrinos, but it's not related to oscillations. But if you even entertain the idea 1 second, whether the standard technique in this field, blame the nuclearis, will work, no, it won't. It has been shown that even if you mess up with the cross-section, the asymmetry won't go away. Okay, so far we have visited all what I call the standard physics, okay? The physics we can dream of. Now, let me introduce you someone which is not a hero, but probably you are too young to know. He is Donald Rumsfeld. He was Secretary of State on the 2 Bush administrations, the father and the son. As a Secretary of Defense, he was Secretary of Defense. Probably he was not the most successful. He was involved in 2 wars and not very successful in either. So, but he explained what phenomenology is all about. For me, he is quite good. He says, there are things you know. There are things you know, you don't know. But there are things, the most interesting things are the things you don't know. These are the good things. So let's navigate the Rumsfeld matrix, okay? So I'm gonna tour you through the Rumsfeld matrix. So we started there with the things we know. We are gonna now explore the things we know we don't know, and we would like to know, but we will end up, hopefully today or tomorrow, talking about what the things we don't know, and can appear there. And this is where the fun is, okay? So let's start with the things we know, we don't know, and we would like to cover in the next years, okay? So there are 4 questions we would like to answer, broadly speaking. 3 of them will be answered by the long baseline program, 1 if not. The most pressing issue, no doubt, is the one we are going to explore tomorrow at length, is whether neutrinos are Dirac or Majorana particles. No doubt about that. This is the most important question we will need to answer in the next years. This is the first question. And there, the collider, the long baseline program, even the short baseline program, will have nothing to do about that. The second question is whether there are sterile neutrinos out there, and if there are, how many of them there are, what are the masses, okay? This will be answered hopefully by the short and the long baseline programs. The third question is, what's the form of the mixing matrix, okay? What, if you want, whether the hierarchy is normal or inverted. We know that the CKM matrix, the matrix in the quark sector, is pretty diagonal. We know already that it's not diagonal in the case of neutrinos. We have said this, that this is basically what I showed you before. We don't know whether the state with the smallest electron neutrino content is the heaviest or the lightest. In this language, this will mean we don't know whether the smallest entry of the mixing matrix is the 1,3 or the 2,1. And this is something we would like to know. And how we are going to do that? We are going to look at what these people in the flavor sector have done. As I told you before, I mean, the physics they have is exactly identical to ours. So we are going to see what they have done and essentially replicate that. I mean, everybody knows by now that the mass of decay long is larger than the mass of decay short. This is knowledge of the 70s. I was wearing diapers when the CP experiment, this experiment was done, okay? So the idea there is to pass counts through matter, which they call a regenerator, okay? And they have beaten the unknown sign of the K long, K short mass difference with a known sign of the regenerator amplitude. This will mean you know the sign of the interaction term, you create an interference. By seeing whether the interference is constructive or destructive, you find out the relative sign between the 2 terms. How we are going to do to find out the sign of the atmospheric mass difference? Exactly the same. Hopefully before I start wearing diapers again, okay? So, you don't know. You never know, okay? So we are going to pass neutrinos through our regenerator, which is matter, okay? And we are going to beat the unknown sign of the atmospheric mass difference with the known sign of the electron forward scattering amplitude. It's exactly the same. The advantage, we don't have to send neutrinos through pipes. We send them through the earth because they hardly interact. What are the drawbacks of that? It's not really a drawback. It's that to accumulate enough matter effects, we need to go to long baselines, several 100 to 1,000 kilometers. But we have seen yesterday, we already have those baselines. What is the fourth question there is whether CP is violated in the leptonic sector. This is what the experimentalists call the holy grail of the experiments. I'm not sure I agree with that. Okay? It's one more parameter we are going to measure. How we are going to look whether CP is violated in the lepton sector, exactly as we did in quarks. Remember when you took your elementary particle course or whatever, what they were telling to you, what do you need to have CP violation in the quark sector? You need all the quark masses to be different. You need all the mixing angles to be different, and you need the three families to be involved. It's exactly the same here, okay? It's exactly, if any of the two neutrinos are mass degenerate, this phase is unphysical. And this is, so how we are going to measure CP violation? We are going to look for an appearance probability in the neutrino channel and compare it to the same survival probability in the neutrino channel and look for any difference. Remember that we have to use appearance and never disappearance, because disappearance, they are forced to be equal by CPT. So this is why we look for appearance. Disappearance will be easier. Okay, so this difference is proportional, as we expect, to the Yards-Lock invariant, to the product of all the mixing angles, except that in our case, the Yards-Lock invariant is not a big suppression any longer, because our mixing angles are large. Our maximatrix is far from being diagonal. So it's exactly the same as here, but notice you have to have the three families involved. But we want to trigger them, but not much. Notice that now this is proportional to the sign of the kinematic phase and not the sign square. So if this average is out, it averages not to a half, but to 0. Okay, so you have to trigger them all at the same time. And this involves very long baselines because the solar mass difference is there. But if you put long baseline, this is a problem because, as I said before, it's a blessing and a curse. Okay, we don't need to send a pipe of neutrinos 1,000 kilometers, otherwise the experiments won't be feasible. But we have the Earth, and the Earth is not matter-antimatter symmetric. This will mean that the Earth, when you send neutrinos through the Earth, you induce a fake CP violation. You will get a difference between the appearance probability in neutrinos and antineutrinos because the Earth is matter-antimatter symmetric. So we have seen this before. You have matter effects. Okay, so even if the space were 0, you will get a difference just because of matter effects. So the challenge will be to disentangle true, genuine CP violation from matter-induced CP violation. There are two strategies to do that, and I'm going to show, but the key point here, at least notice that they have different energy dependencies. The two terms have different energy dependence, so you have a chance there. There are two strategies to attack this problem, the Japanese strategy and the American strategy, so we are going to explain them both. The Japanese strategy is, okay, if matter effects, is very Japanese, if matter effects are a problem, keep them low, okay, go to short baselines. Short means in this case 200 kilometers. Okay, this is short, but then do something really, really radical. Okay, go off axis. Going off axis sounds like a completely crazy idea because it means point your detector somewhere, point your beam somewhere, and place the detector 10 kilometers away. And you think this is a completely stupid idea because you are missing most of your signal. This is true, you are missing most of your signal, but it can be shown that in the off-axis detector, the energies of neutrinos you get are narrowed down. They are almost a monochromatic beam of very low energy neutrinos. And for this particular window of low energy neutrinos, you get way more statistics than the one you would have gotten in the on-axis beam. And by going to low energy neutrinos, you increase the ratio L over E without enlarging the distance. So it's a very smart idea. It's a very challenging idea. The American strategy is very American. Most of the European groups are in the American strategy. The American strategy is related to the Dune experiment. It's very American. So it means if you cannot deal with matter effects, embrace them all. Go to very long distances, 1,200 kilometers, okay? But go on axis to a very broadband beam. If you go to a very broadband beam, you have tons of statistics and you can see the spectral distortion. And by seeing the spectral distortion, you won't tell genuine CP violation from matter-induced CP violation. Okay, this is the idea of the experimentalist, and this is the plan. But for us, as I said, the important things are not the known unknowns, but the unknown unknowns. What can go wrong? I know that we are ruining these people's lives, but it's okay, okay? Because, and don't get me wrong, what I'm saying is that, I mean, this is the plan, but if things go wrong in the right way, it's way more fun. And all of you will land jobs, you know, if we find new physics with that. If you find CP violation, it's gonna be one parameter more, fine, cross, we measure that. But if we find something radically different, it will be way better than that. Although this problem would be ruined, okay? Okay, they won't measure CP violation, fine, okay, who cares? We will measure something more interesting than that. So what can go wrong? I'm gonna start adiabatically. Okay, so I'm gonna start adiabatically all the things that can go wrong. Okay, first of all, you can have sterile neutrinos. This is pretty mild. I mean, I'm playing Snow White here. Really, I mean, I cannot be, you know, more mild than that. You can have sterile neutrinos. So if you have one more sterile neutrino, you have one sterile neutrino on top of the 3 active neutrinos, how many mixing angles and phases you have? 6, one sterile neutrino, 6 angles and 3 Dirac phases, okay? You know, life gets complicated, but you can simplify your schemes a lot. I'm gonna go the most simplified. This is the muon neutrino survival probability. We have seen all the way here. And if you have one additional sterile neutrino, in the most simplifying assumption case you can have, this is the 2 additional contributions you get for the muon neutrino survival probability. Okay, you have 2 new mixing angles, you can, and 1 mass difference, you can not get rid of no matter how simplified you are. And what is going to happen, I'm going to show you, I mean, really briefly what happens. This is a very complicated plot. Let me show you, walk you through that. This is the survival, the transition probability as a function of L over E. And these long baseline experiments, they have a near detector and a far detector to cancel systematic. So the gray region is what you are going to see in the near detector and in the far detector. And in the upper level, I put the true neutrino energy, which goes all the way the other way, okay, left to right. So as you can see, you don't have to see all the plot. The black line, let me show you, see there, this is easier for me. The black line is the muon neutrino survival probability if there are no sterile neutrinos. And the blue line is what you would get if you have one sterile neutrino whose mass difference is 5, 10 to the minus 2 electron volt square. So you see you have a pretty decent sensitivity in the far detector plot. If you increase the mass a little bit, 1 order of magnitude, the mass difference square, 1 order of magnitude, you start getting sensitivity in the near detector. If you increase it even further than that, you have a lot of sensitivity in the near detector. You kept the sensitivity in the far detector because essentially for masses this high, the near detector is like a short baseline experiment. So all in all, the Dune experiment will be able to see whether there is a sterile neutrino there. Of course, this is very competitive to what the short baseline program will do. But what would happen if phase space to oscillations is closed? If you have a sterile neutrino, but your sterile neutrino is just heavy enough not to be able to oscillate directly into sterile neutrino, are you gonna miss it? No, you are not, because, okay, you are not gonna see it directly because, as we said, phase space to oscillation is closed, but it's still gonna be there. This will mean that the mixing matrix will still be 4 times 4. But you are parameterizing all your oscillation as if it were 3 times 3. So you are going to see the violations of unitarity. It will reflect in your analysis as violations of unitarity. And this is extremely important. Why? Because you are extracting the angles to measure CP violation, assuming unitarity. Okay, so if you have unitarity violations, they can be incorporated in this way. This is the standard matrix you use, and these are the violations of unitarity. If you have seen in the quark sector, people talk about unitarity triangles, and they see the violations of unitarity as the unitarity triangles not closing, okay, leaving open. We are using a different language here, but you are doing exactly the same. These A alpha parameters there are what is the gap for the triangle not to close. It's essentially this thing, but it's exactly the same. And if the matrix is non-unitary and you keep ignoring that, if you don't do the analysis right, this will completely compromise the program you have to measure CP violation. So you need to check first whether unitarity is or is not there, and then you can go ahead with your program. Because unitarity may be violated because, for example, for the presence of sterile neutrinos. Now we move a little bit further away. We talk about non-standard neutrino interactions. Non-standard neutrino and I will stop after non-standard interactions. Non-standard neutrino interactions are not any interaction you can dream of that is not contained in the standard model. We wish they were, but they are not. They are just those interactions that we parameterize in this 4 Fermi effective Hamiltonian, which I have factored out. G Fermi for you, this epsilon then will explain to you how strong or how weak your interactions are compared to the standard weak interactions. But we know nothing about these non-standard neutrino interactions. They can happen at any stage of the process. So in principle, you have to break down your analysis into non-standard neutrinos interaction at production, non-standard neutrino interactions at the propagation or the evolution, or non-standard neutrino interactions at the detection. However, non-standard neutrino interactions at the production and at detection, they involve a charged lepton. Okay, so they have been bounding most notably by meson decays, and they have been bounding for the epsilons to be 10 to the minus 2, 10 to the minus 3, depends on the channel. So they play no role. They are not important for oscillations. In oscillations, we are left with what are called neutral current non-standard neutrino interactions, or neutrino interaction, non-standard neutrino interactions in the propagation. And they can be incorporated into the Hamiltonian of neutrino oscillation in this way. And this should ring a bell in your head, please. And more if you see the one there, because we are incorporating them exactly in the same way as we incorporated half an hour ago matter effects. Okay, if you put this there, because they have a similar effect to matter effect. You cannot think them as neutrinos propagated in a medium made of electron muons and taus, but it's not that different from that. So, but for us to make the analysis, let's go back to the 2-flavor formalism, which is this, and we have seen that everything proportional to the identity matrix will go away. So we can take this E mu to be 0, and this will be the difference of the two, and take this, the off-diagonal parameter to be real, because we take the other one to be 0. This one is unphysical, the phase is unphysical. So we have only 2 parameters parameterizing all the non-standard neutrino interaction, a diagonal term and an off-diagonal term. And now we see what these terms do to you. This is the muon neutrino survival probability we have using on along. How we extract measurement from this muon neutrino survival probability. We, as usual, we measure the ratio of observed over expected events. We see the depths of this dip of the first maximum of the oscillation probability, and from this depth we extract the mixing angle. From the position of the depth of the dip, we extract the mass difference. So what would happen if I include non-standard neutrino interactions? If I include non-standard neutrino interactions, the off-diagonal term will move where my minimum is located. So it will affect the determination of the mass difference, okay? But these are like matter effects. So it will shift the mass difference one side for neutrinos and the opposite side to anti-neutrinos, okay? This behaves like matter effects in this respect. And the diagonal term will change the depths of the dip. So they affect the determination of the mixing angle. Again, one side to neutrinos and the opposite side to anti-neutrinos. And then this is what non-standard neutrino interactions do for you. Now I stop here, and tomorrow we are gonna do one thing, only one thing before going, okay? Tomorrow we are gonna talk a little bit about CPT violation. So first of all, before tomorrow, let me talk to you why nobody ever talks about CPT violation. Why people hate it. I mean, I'm not sure hate. They have prevention. CPT violation is one of the sacred cows of the standard model, of physics in general, high energy physics in general. So why to chop a sacred cow to hamburger? Okay, what is the idea behind that? I mean, the idea behind that is the CPT theorem. Why we love it so much? Because the CPT theorem is based almost on nothing. Okay, it says that any local relativistic quantum field theory that respects Lorentz invariance automatically has CPT built in. Okay, this is why we respect CPT so much. But this means that if you test CPT, what you are testing is not the standard model. Okay, this is important to keep in mind. What you are testing is the framework, the tools you use to describe high energy physics in general. Okay, so this is why it's so important to test CPT violation, because it's not messing around with the standard model. It's challenging the possibility of describing nature to some extent in terms of local relativistic quantum field theories. And this is why CPT is so interesting by its own. Because to some extent, it can shake the whole paradigm and not just your standard model. Okay, I continue tomorrow. Thank you.
Thank you, Gabriela. Do we have questions?
Thanks a lot. So in your last slide, you mentioned about yes, this one, about the NSI, right? In the oscillation. And then you described that for neutrinos, you shift in one way, the dip, and for antineutrinos, the other way. So this is a form of CP violation as well, right?
This is a form of, okay, these are matter effects, okay, yes. If you have them, I mean, if you, okay, yes, in principle, yes. If you want to extract, is CP violation, is matter, is medium-induced CP violation, yes. So if you take CP violation as a difference in the probability of neutrinos versus antineutrinos.
Yes, yes.
Yes, it will.
So you still have to distinguish between a true CP violation and an NSI, for example.
Okay, this is not quite true, because if, in the sense that NSI are already bounded, because, for example, we haven't seen NSI from, I mean, if you see that they behave like matter effects in the sun, for example, we have already bounds. It's different than matter effects, because we already, NSIs will happen all the way. So we have strong bounds on NSI. It's true that if people have constructed, I have a lot against that. People normally bound NSIs one by one. So they assume they are all zero but one, and bound is one. And then they are also, this is not bound. If, what I would say is, if you put all of them on at once, there are no bounds. So what you are saying is absolutely true. In principle, you should be able, but however, NSIs, if they exist, go how to hand with matter effects. So by the spectral distortions, you can tell them from true genuine CP violation. This is easy. Okay, so it's because they have the same spectral distortions as true matter effects. So in principle, this can be done. It's doable, not easy. I say it's easy, and my experimental friends hyperventilate, you know. No, it's not easy. It's not easy. It's feasible, you know.
Thanks.
You're welcome.
Any other question? I'll ask one question. So you said sneakily earlier that for delta CP to matter, theta 1,3 needs to be 0.
So for me, physical.
Right,
Yes.
and that is of course true. But really the statement is all of them need to be non-zero.
But the other two were non-zero from the 80s. You know?
Okay, yes.
Okay, it's true. The three, I mean, and all the mass difference have to be different from 0. The two mass difference have to be different from 0. But I'm saying only theta to 3 because the atmospheric mixing angle and the solar mixing angle were different from 0 when these kids were born. Okay,
Right.
not when
So-
I was born.
So my question is, when we plug the delta CP next to the theta 1,3 in the PMNS matrix, we could have plugged it anywhere else in the solar sector or in the atmospheric sector. The fact that we put it next to the theta 1,3 is because, as you said, it's the one that we didn't know. But when was the PMNS matrix prescription invented, quote unquote? So what really prompted us to put it from the beginning, the delta CP next to the theta 1,3.
Yes, I think the answer there is the CKM. This is how it's done in the
Oh,
CKM.
okay.
This is how it's done in the CKM. So essentially, I mean, it took us, I think, we call it PNMS just. In the very beginning, we call it the leptonic CKM. So, but then it evolved to the PNMS. But I think they put it there. You can see in the CKM, it appears in the 1,3, and then we inherited from there. So I think from the very beginning, as far as I remember, it was there.
So it might have been a lucky accident.
Yes.
Okay, thank you. Any final question for Gabriela? I don't see any hands. And Marcus, is there anyone online?
I don't see any hands.
Okay, then let's thank Gabriela again. And we break for lunch until 1:30.
So we have set just again, in order for